Hello everyone, webinar, New Trends in Power System Modernization. This is Kainat Padma, Chairperson IET on Campus NED. And now I would like to invite Sir Essackjee Ismael to present.
Okay, maybe we missed a few words from you, maybe due to the internet connection. I'm just going to start the presentation. So thank you, Fatima and the team from IT Campus NED from Karachi. It's indeed like a pleasure to be having me for maybe presenting a few of the trends in power system modernization. So thank you for all participants for being here, for having registered for this webinar. Hopefully, I will be able to give you an idea about what are the new trends in power system modernization. I'm just going to admit a few more people as they come in, and let's get moving. Okay, I'm going to go into the presentation mode. Okay, that's it. Let me just pin this one. Yeah, so if you have any questions, you can write it down in the chat box, and later on, maybe at the end, we are going to get back to the question. So who am I? I'm a senior engineer at the Central Electricity Board, which is the public utility in Mauritius concerned with power system generation, transmission, and distribution. So we have only one body which takes care of the whole system, generation, transmission, and distribution, as compared in some countries where it is split. Okay, so unbundling, but here the country is quite small. So I'm like a senior engineer. I'm responsible for transmission project in the country, most, or if not all, or what we call transmission project from inception to the commissioning. But I'm so involved in lecturing at different universities, maybe 4 or 5 universities down the past 10 years in and around Mauritius. And besides, I'm a coach in personal development and leadership. So I may be reached on my email address or on my contact number, or I have also a website where you can have more information on myself. So where is Mauritius? Maybe for those who don't know where this small country is, let's have a quick look. Let me just go back quickly. So we are here in the Indian Ocean, okay, a very small island. And let's have a quick facts about Mauritius. Okay, there you go. So the capital is Port Louis. The population is 1.2 million from Indian origin, African, Creole, and Chinese. And just to compare from our population, which is 1.2, let's have a look at the size as well. Nearly like 2,000 kilometers square, okay, as compared to Karachi, which is like 2 times the size, but the population of Karachi is nearly 15 million as compared to Mauritius. So one of the highlights of this country is it is the only known habitat of the dodo, which is now an extinct bird. So it is the only place on earth where this animal, this bird actually lived, like it was like a couple of centuries ago. So this is a bit about Mauritius. Some ground rules for today. Okay. Everyone is going to be on mute just to avoid any feed forward or amplification of noise and so on, just to have everyone having a pleasant time in this presentation. You can ask questions in the chat box. Feel free. Hopefully, I'm going to go through it fully at the end. This session is being recorded with your permission, and the recording will be made available just in case you miss anything. It's going to be made available to you later on. We have your contact details. And it may happen that internet connection gets disconnected. We don't know what can happen. It can be like a power cut and so on, but don't worry, we're just going to reconnect again. This is part of the virtual world that is a new normal for today. So that was it for the introduction. Let's get started about what we have on the menu for today. So we are going to see modernization of the power system. Yes, what do we mean? What are the needs to go for modernization? Is the current infrastructure, the power systems that we have currently, not enough for us? Why do we need? So we're going to have a look at the needs for modernization, the drivers for modernization, and then the enablers. What are the technology or things which are there to enable this modernization process? Then we are going to have a look at the generation sources, which comprises of renewable energy, distributed generation, battery energy storage, virtual power plant, microgrid electric vehicle. Definitely, it's going to be like a 1 hour or 90 minutes at most, hopefully not too much, but we're just going to have a quick look. It's just going to trigger a few things for you. If you're interested, you can go deeper or you can get in touch with me, because we won't have time to go like deeply into all these technologies, but we're going to hopefully to give you at least the basics that you will need to be having to be able to understand it fully and maybe fly from your own from there. Next is going to be about power lines. So modernization, the generation sources. Next after generation is how do we need to evacuate this power? We have power lines. So we are going to see technologies, new things happening in active management of power lines. GIS is not the substation. It's mostly about the geographical information system. How we are planning nowadays. We don't use the paper plans or map. We are using another level of information system. Then we have the operation and maintenance, which is about the cost. How can we minimize cost? Because ultimately it is the end user who is going to pay for whatever operation and maintenance costs are. Then we have ADMS, which is Advanced Distribution Management System. We are going to see the flexible AC transmission system, and then a quick look at metering. What are the new things happening in terms of metering? I think I will need to slow down because I tend to speak very quickly. So next, it's going to be about the concern. Yes, we need to modernize, but then we do have some concerns which are coming up into play, into the arena, into the play field of this modern power system, which we are looking for. And then ultimately, we are going to discuss about, maybe share a few pictures about what is meant by grid resilient. Okay, new things are happening. There are new, maybe concern in terms of weather. So is our grid ready to take care of these new happenings in our environment? Then in terms of conclusion, we are going to see new players as well, what needs to be done in terms of regulation. So this is basically what we are going to have a look at during this 1 hour or slightly more that we are going to be together. So let's get started. So the purpose of power system is to supply electric energy satisfying the following constraints, which is reliability, safety, affordability. So these were initially, when the power system was being set up, were initially like, I don't know, maybe 60, 70, 80 years back, when we were trying to come up with, there was a war between, maybe you have read about that, the AC and DC war and so on. So transmission, distribution was ongoing at that point in time. So reliability means ability to limit interruption. You can't have an interruption every hour or so. So how can we limit interruption? Then we have safety, that is minimize equipment failures, danger to people. So it's about, this is what we meant. I think it's a general term for safety. It's about making sure that people don't get injured or equipment are not like damaged through the process of distribution of energy or generation of energy. Then affordable means to minimize the cost, the operation cost, such that even the production of energy, the distribution and transmission, so that the customer needs not pay extra. So the least maybe cost, unit cost for generation of electricity and supply. So this was when the transmission system, the distribution system, the grid was being set up, this is what it was targeted for. But have a look at now the purpose of modern power system. We still have reliability, we still have safety, we still have affordability, but then we have got security, which is about building a robust, system which is able to withstand physical, like man-made disasters. It can be like an accident or even cyber threats. We are going digital. So we may be having cyber threats or hackers on the system nowadays. We are going to have a look at that in one of our slides. We have providing a flexible power system. What is meant by flexible? It is an ability of the power system to absorb or to integrate distributed generation, what we know as renewable energy, electric vehicles, Okay, it's coming, not only vehicles, but it is not only cars, but vehicles as such, it can be trucks and so on. And then we have battery energy as well. Then we have resilience. What is resilience? About withstand damage from major disruptive event. We can have huge power cut and so on. So is our grid resilient? It can be lightning. Okay, as you know, we have climate change, which is contributing to have maybe super cyclone, like flash flood. So is our network able to withstand, to be resilient to these happening? We are going to have a look. And then we have signed, every country, most countries have signed the Paris Agreement, the Paris Protocol, which says that we need to proceed with decarbonization of our world in terms of energy and then transportation. So we need to go for clean energy, which we usually call renewable energy, embracing renewable energy. So the grid, as it was designed, this is how it was designed and how this is a new requirement. So you can see the difference. There are new constraints. So we say that it's a confluence of factors which is driving the need for modernization. The grid was not built to satisfy all these new factors, characteristics. Okay, we need to maybe change to enhance our grid to be able to cater for all these characteristics. So what are the drivers? First, as we mentioned, it's about the decarbonization. There is a willingness, it's a global willingness because it has a huge effect on climate change. You can see the heat is going up, the icebergs are being melted and so on. So there was a Paris Agreement signed in December 2015, where all of the countries which were present, which form part of this agreement, it is actually a legally binding international treaty on climate change. I have included the link below. Anyway, these sets of slides are going to be sent to you. I'm going to send it to Fatima, and she's going to send it to you by email. You're going to have all the information, all the links, all the necessary links for you to probe into. So this agreement is binding to all those who have signed them. It was signed in December of 2015, and it entered into force in November 2016. The goal is to limit global warming by 2 degrees or 1.5 degrees before industrialization happened. So it's a huge maybe goal that we need to do, and it's like it can't be only one country who is willing to do that. It needs to be like a huge, like each and everyone working hand in hand to be able to achieve such a goal. Else, if we're not able to achieve this goal, the global temperature of the earth is going to go up, and is going to affect the natural fauna and fauna. We have the iceberg and so on. So it's a catalog of problems which can happen after if we don't like work towards achieving some of the goals of this like low carbon emission, such that it's going to affect to limit the problems on our world. Next, we have a driver which is digitization. How can we like use the new things which are happening in the digital world? Everything is going to digital. We are moving from analog to digital. Okay, so we need to, these are drivers are pushing the modernization of the grid. Next, we have decentralization. It goes hand in hand with decarbonization, because we need to integrate renewable energy to be able to move away from fossil fuel, heavy oil, production of electricity from these. So we need to have more of renewable energy, some of which are mostly popular: PV, photovoltaic, and wind. But then it's not the utility who has the investment, the capital expenditure to install all these. So they are going towards what we call decentralization. Initially, power was produced traditionally from maybe nuclear power plant, heavy oil, and so on. So we're centralized, okay, centralized, huge power, bulk power, then transmitted to load centers and so on, far from maybe where they are being produced. If you had a huge hydropower plant, because you can't have a hydropower plant in the middle of a city, it will depend on where it is localized, the position, if you have a heavy oil, so it maybe needs where you are getting the heavy oil, you're extracting that, or next to the port where the ship is coming with a heavy oil. So they have been positioned in centralized position. Nowadays, it's more towards decentralization. So these are some of the drivers of a modern power system. Now, the role of electricity in our daily life has changed. Try to agree or disagree on this thing. Is it true that the way we are using electricity nowadays is the same as what it were for our parents? Most likely it was used for lighting, to have a bulb at home, just to light. But nowadays, just have a look around you. We are using a laptop, a PC, a tablet, or even your mobile phone. You are using Wi-Fi. You have lights on your head. You have you're in an AC room. All these things are working on electricity. Just think about what can happen if we don't have electricity for a short amount of time. No Wi-Fi, so no Facebook, no of these social media, and even maybe if you have a water pump, which is like pumping water throughout the house, you won't be able to maybe use it for cooking, for washing clothes, or for even going to the toilet. Okay, so electricity is now an intrinsic part of our life. We don't see it, we don't feel it, but it is each and every part. It's like an octopus sending all its tentacles across the different spheres of our life. Okay, it can have just an example in terms of industrialization. Previously, we had the industry 1.0, where it was a steam plant, mechanical, okay, for cultivation, for whatever, for in the industry. Then we moved towards electricity, which was an industry with machines and so on. Then it was electronics getting in. Nowadays, we are talking about industry 4.0, where we need robotic, not only robotics, but advanced robotics, 3D printing, Internet of Things, artificial intelligence, big data. All these, as from industry 2.0, 3.0, 4.0, there's amplified use of electricity. This is only for industrialization. How about health? How about education? Nowadays, we are talking about, because pupils, like students, can't attend classes like they have been doing in the past, so they need to attend it virtually. Students, even from primary schools, they need to attend use Zoom for classes. In Mauritius, the schools are closed due to the pandemic, but education has taken another step, and they need electricity, which is like a common denominator towards that. How about transportation? Okay, we had the trains in the past. Nowadays, we have metro working on electricity. We have buses which were running on fossil fuel. Nowadays, we have buses which run on electricity. Even cars, definitely we're going to have a look at that. Playground, in the past, but kids were playing around in football ground, on playgrounds and so on. Nowadays, they're on the tablet. Okay, so electricity has changed, maybe for the right, for the good or for the bad. This is not the sake of the discussion today, but it has changed the way we are living. Okay, so what we have is that we need to have a look at new solutions to all problems. So we have all problems, but nowadays we have these drivers, these enablers, which are going to provide us with new solutions. Or we can have solutions to new problems which has cropped up recently, and we need to provide solutions for that. So let me just admit a few people in again. So we are requiring the electricity system to perform in ways for which it was not designed. It was not designed to be able to tackle all that. It was designed to just light a bulb, run a motor. That was it, that's all. Nowadays, it is part of our life, okay? You can't manage what you can't measure. Okay, you can't manage what you can't measure. So we will need to, what does this means to us? We need to add sensors. We need to add intelligence to the system so that we can take decision. We can manage the grid. So one of the things that needs to be in place for modernization is about adding sensors, adding new components to the system. Let's have a look. So how are we going to proceed? We are going to use a why, what, how approach. Why do it? Why do we need to go for modernization? What should be done? What should be done for us to be able to manage a modernized grid? And then how do we do it? how do we achieve what we want in terms of a modern grid. So let's have a quick look at new solutions to all problems. Transmission capability. So all through time, since inception of transmission line and power system, the utilities around the world have been trying to increase transmission capability. I think we lost it shortly. It was maybe, again, the use of electricity nowadays. Let me just go back to the slide. Let me close the slide first. Then we go back. Okay, there we were. Let me just present that again. Let me pin that. Okay, so we were speaking about the, oops, a few more people getting in. Okay, so we had a transmission line. Okay, we had towers, which in most countries you have. So we had conductors from here to here. Now, if we need to increase, oops, a few more people getting in. Okay, if we need to increase capacity on this transmission line, so we'll need to look for bigger conductor. Maybe this was a conductor. We need to go for a bigger conductor, much higher current carrying capacity. But then these towers, if we increase the size, we are going to go for a bigger conductor. We won't be able, because these tower lines, they have mechanical structure. They are limited by the load that they can sustain. So what's going to happen? Okay, if we install a bigger conductor, it's going to most likely sag. Okay, and the ground clearance is going to be affected. Okay, we won't have ground clearance. And these towers, they are going to be mechanically stressed, and they can even rupture. So what can be done? How can we increase this current carrying capacity while keeping the legacy system, this transmission line? So we have nowadays, let's have a quick look. Oops. A few more people getting in. Okay, nowadays, like what you call material science, advances in material science. So on the left, you can see the conventional steel reinforced conductor, which we call ACSR. It is used in some countries. In Mauritius, we don't use it since we have a coastal, we are a coastal island as such, and we have a lot of corrosion happening. So we don't use a CSR, but in most countries they use that. So in the middle, you have reinforced steel, which is going to provide the mechanical strength of the conductor. Next to it, you have aluminum and aluminum alloy, which is going to provide the electrical conductivity. What have they done? They have used much better quality of aluminum. So what is much better quality of aluminum? Is that they can carry much more current. And you can see here, the weight was, these are strands, what you see on the, let me just annotate that. These are strands, okay, easy to build. But then in between, what can you see? There are spacers, which are not used. Okay, now here they have used a trapezoidal approach so that it is much compact. So the same size of conductor can now carry much more current. And they have replaced this steel reinforcement by a fiber, carbon fiber. This is going to give you the mechanical strength, and this one is going to provide the electrical properties. Ultimately, you have a new conductor, most likely the same size, which is able to carry much more of electricity. Okay, let's have a quick look. So the added aluminum content and quality increase the conductor's current carrying capacity. By how much? By maybe twice that of the conventional conductor. So you can double your transmission capacity. I have been reading a bit about Pakistan. Pakistan is not a country where you lack renewable, where you lack generation capacity, but there is a limitation on the amount that you can transmit. Okay, so if you go for such types of conductors, definitely you can increase, you can solve your problem of transmission capability. Okay, it has been, I think, less than 10 years. It's a new material which has been, not material, but maybe technology, which has been in place less than 10 years back. So it's quite new. And so you can double your transmission capability. And you can decrease your line losses by 25 to 40%, depending on how much current you're carrying. Isn't that interesting? So you can use the existing system. You just replace the conductors and you double your transmission capacity while reducing your losses. Okay, losses is a very important parameter because it's going to see how much losses is, how much are you producing, the unit produced and unit sold. What is in between? Let's say you are producing, let me just annotate that again. Let's say you're producing 100 units, this is generation, and you are selling 60 units. So what in between is you are losing 40 units of energy. So it is part of the system because every current carrying conductor is going to lose heat, maybe power in terms of heat, but then in transformers as well, you have a few losses. We are going to see that hysteresis and eddy current loss. But then if we try to, can we decrease this like losses? Yes. Mauritius has gone from 30 to nowadays we are on 6% of losses, 30% to 6%. A lot of strategies have been put in place. The average across the world is around 9%. Okay. And if I'm not mistaken, Pakistan is around 20%. So there is room for improvement. How to bring that down, and such like new technology can help you. Conventional conductor, you can reduce your line losses. So the improved efficiency, okay, is going to characterize the current, definitely as we said, and then without excessive sag. So you could have done the same with using a bigger size of conductor, but then the sagging would have been much more. This conductor would have been here because it is heavier. When it sag more, you have less clearance, is safety. You're compromising safety. Remember, one of the characteristics that we mentioned about safety, very important. So this is it. So it's an old problem, but you have a new solution which is now applicable. The second one which we are going to see is losses in transformer. If you know a bit about transformer, you have two main losses. You have the in the core, okay. You have the conductor loss as well, I squared R, but then in the core you have you have the hysteresis and the eddy current loss. So the core of the transformer is made of lamination, very thin lamination to limit eddy current loss. But the material they use for the core is important. Again, material science has come up with new materials lately. They have been using silicon steel for I don't know how many years. This has been traditional silicon steel. So this is a hysteresis curve. Okay, when you are energizing the transformer, it's going to go along this way, then it's going to be this way, and as it changes polarity and so on, then it's going to be this way. Okay, whatever is inside is going to represent power loss. Okay, this power loss, let me just write it fully. Power loss due to the reversal of magnetism in the core, because we know AC is changing. Every time it is changing direction, it's going to reverse the magnetism. And every time it is reversing magnetism, we are going to find this amount of losses in the system. But we can't do otherwise. It is in the system itself, it's in the transformer, and transformer are important component of the power system. So what can be done? By changing the material, using a new material. Let me allow a few people in. Okay, by changing the material, we can squeeze this area. Here it is. We are going to start here, like a 0, we magnetize, then we go around this loop. What can you see now? What is this area? Let's call that area A. This one is area B. So area B is much smaller than area A. Now you have decreased the power loss in your transformer, and you have so many transformers in the network, so many. Okay, and it forms part of this advantage of using AC, that you can step up and step down easily. So you have so many. So if we shift ultimately or slowly towards amorphous alloy for the lamination, it can give you like much better losses. Okay, decreased losses in the transformer. Okay, a few literature for you, but we are already explained that. So how about the enablers now? If we talk through these two examples, we have many more examples, but we haven't taken the need to, or due to material science, advances in material science. We have communication. We mentioned about sensor, what you can't measure, you can't control what you can't measure. So how can we measure things all around our network? we need to have a good communication. Nowadays with fiber optics, this has enabled the power utility, or this is enabling the power utility to have much communication, good communication, real-time communication with the different sensors that they have and so on. And then definitely we have technology, which is playing a big role. Initially, maybe sensors was going to be very expensive. How can we mount? Maybe the size was going to be very large. How can we mount that on a pole? And so nowadays, due to miniaturization, it has become smaller. Maybe it can fit onto a small module. You can install that. You can, about the Raspberry Pi and so on. Small, like thin, like components which can do a lot. You can have so a myriads of opportunities opening up for us. Okay, this is I'm just using the example of the Mauritian power system just to give you an idea. So we have the power generation. So this is a generation part. Then we have the transmission. Okay, power is going to step up. We are going to step up voltage to transmission level. In Mauritius, we are using 66 kV. I know that most likely in Pakistan, you are using 400 or maybe more. Okay, then we'll go towards distribution. Okay, towards our load centers and so on. And then ultimately we have the customer at the end. So how does energy flow? Traditional power system from generation to the customer. One direction flow of energy. What is a data flow? We have communication between only generation and transmission because it was costing so much to be able to provide data communication to distribution and so on. It was because distribution is all around the country. Each houses we can say, so how can we communicate with so many houses? It was difficult, but nowadays, as we have seen, there are enablers which will help us to do so. And then payment was one way where it was an end customer, which was like who was paying the utility. It can be the distribution company, transmission company, or the generation company. So it was the reverse way for payment. In Pakistan, based on what I've been able to find, so hydro represents 29% of the generation, thermal 61%, nuclear 5%, and then we have some renewables like bagasse, wind, PV, and so on, which contribute to 5%. So we have a look, we have only thermal and nuclear, which are what we call the fossil fuel, or not fossil, but nuclear is like in between, but it's not regarded as a renewable energy. So we have 29 and 5, which are around 34%, which comes from like clean energy, we can say. Then remember this graph. Oops, let me just go back a few slides. This graph. So we can introduce distributed generation. Okay, we can introduce power, additional power. This is what we call distributed generation at different instances. We don't need to have it centralized nowadays. Okay, as we mentioned, hydro needs to be near to maybe a difference in height to get the falling water, the energy from the falling water. Maybe a geothermal needs to be where you are able to get this power from the earth and so on. But nowadays with this renewable power, we can have it in different places. Oops, what's happening here? Call me daddy, what are you doing? Let me just close this first. Oops. I will need to stop the share. Now I'm going to share again. Okay, there we go. Okay, so we can add renewable energy at different places in our transmission system. So for instance, this is a concentrated power where they're going to focus all the rays onto one tower and then collect the heat from over there. You can read about that. You have offshore wind turbines or wind, but PV farm. It's not a PV rooftop, but a farm. So it's huge. And the energy there is going to be connected to the transmission network. So these type, we don't call them distributed energy. So these are large-scale renewable energy sources connected to the transmission network. It's not connected to the distribution network. So these are still what we can call centralized power plant because of the amount of power that they produce. They are going to be connected onto the transmission network. So these are not considered as distributed generation because we are going to maintain control with them. We can have real-time communication because we don't have so many of them. We can control them. The issue is going to come when they're connected on rooftop or what we call a distribution network. Here's an example of a rooftop photovoltaic system. And then we have what we call, maybe you have not heard about it, which is the vertical axis wind turbine. Okay, maybe you know about the horizontal axis wind turbine, which is like a fan and it's going to create noise. It's an ISO. Okay, for most of you it's an ISO. But then this vertical axis wind turbine is going to be, okay, is going to make up for the sound. It doesn't make any noise. It is good looking, not to an ISO as such. And what is beautiful, okay, I've not included that because it would have been too much. You have nowadays building, if I remember the term, building augmented wind turbine. What is this technology? That you integrate these things, okay, in the structure of the building. You won't see it as a standalone. This is maybe retrofit the building, or they just put it there. Nowadays, they have it integrated in the building, and it produces power around the. You don't need, like for vertical axis, for horizontal axis, you need specific power, wind from one direction and so on. This one we have wind from any direction is going to work. And then wind augmented, that you design your building in such a way that it's like a funnel. Power is going to be converging toward these wind turbine, and you're going to have much bigger. I think an increase in power from 25 to 35%. You have a few buildings already doing that. You have one in the UK, which is satisfying the requirement of the building itself. Okay, and then I think you have one in China or Hong Kong, or that one or two. But there are some, look for these terms, building on augmented wind turbine and vertical axis wind turbine. It is replacing the traditional that we call like this one. Okay, please don't write on my slide. I will need to stop the presentation. Johnny, okay, let me just stop. I will need to clear this one and then reshare again. Okay, let me just. Okay, there you go. Okay, now what has happened? It has created like an energy market, because remember, let's have a look. We have generation, transmission, distribution, generation, transmission, distribution, customer, the flow, the data flow. Now it has changed, because since you are connecting, you have a rooftop PV, the utility needs to know maybe how much power you're producing, maybe have control as well. Is it feasible or not? We are going to see that later, but the utility would want to know how much power you're producing, so that ultimately the role of the control center is to match supply and demand. So the customer here is need to have bidirectional data flow. Power flow as well, it was top down. Nowadays, you can have bottom up as well. Customers producing power and sending maybe extra to the grid. Payment as well, you have tariff structures, what we call built-in tariff, and then not built-in, but feed-in tariff. Okay, so the extras that you're selling, you're exporting onto the grid, you can be paid for that. Instead of you paying the utility for energy consumption, it may turn up that the utility is now paying you to use your energy and to the extra that you're exporting onto the grid. So it creates like a new paradigm. It's like an energy market which has come into play. It's not called a consumer now, it's called a prosumer. You're not consuming, you're producing. It's like in between, you're consuming and producing. We call that a prosumer. And that's what we call a virtual power plant as well. What is a virtual power plant? It's just like, let's say in an area where the utility can't control each and every one, because it's like huge data. Let's say you have 1 million people who have installed photovoltaic on the system. They can't have all that information getting to the control system. So they're going to control that from regions. Maybe region A, maybe you have 100 of PV plants. So it's going to be like a group control. So all the information gathered to one point, and this one communicate to the control center. So it's going to be less amount of information. But then if the control center need to shut down part of that, they just shut this group, all of them are going to be disconnected. So it's like what you call a virtual power plant. Let's say 1 kilowatt, 1 kilowatt, 1 kilowatt, instead of it being 100 kilowatt, it's going to view it as a power plant of 100 kilowatt. Instead of 100 units of 1 kilowatt. That's what we call a virtual power plant. It's going to help into control of the power system. So we have the prosumption device, so the meters needs to adapt. And then you have, anyway, we're going to come back to the energy management system shortly after. So this is coming interesting now. Okay, the system has changed, the flow has changed, load dispatching and load forecasting. Okay, I think this is done. So plan generation, you have, it was a function of demand forecast. How do we know? The ultimate aim is to balance demand and supply for the control center. How do they plan for the generation? They are going to base themselves on what was the demand for the past days, or do we have like a specific, maybe a trend which was set up? Okay, I'm just muting someone. Okay. Okay, this was like, it was quite easy. Okay, Aisha, please be careful with your mic. Okay, so these were based on, okay, these were based on pulse demand. Then what happened? It has only one parameter. So you can focus using one parameter in the equation. You can focus, you can base yourself on what has been happening in the past, you can focus. But when does it become complicated? When you need, nowadays, you don't need to base yourself only on the demand. But what about the PV? How much power can you get from the PV? PV and the wind. And best is battery energy storage device. These as well can provide power, and PV is changing. Wind as well, you don't know, you can't plan exactly how much power you're going to get. For a traditional power system, powerhouse, let's say based on nuclear or heavy oil, if you put it on 50 megawatt, you are going to get 50 megawatt. It's going to be like, you have a few of group control and so on, but basically it's going to be constant throughout. But then for let me just check the chat for a few minutes. Okay. Anyway, so plan generation nowadays is going to be based on all these things. So now it's going to be much more complicated because we have several parameters on hand. Okay, let me just check. See, just give me a few minutes. Okay, that was it. Okay, gone. Okay, let's continue. Plan generation. Let me just check the chat. Okay. Okay, so troublesome person has been kicked off. Anyway, let's focus. Now, this is our guy from who is trying to do the load forecasting. He needs to have data from weather. What is the weather going to be like, which is itself like complicated. Yes, so battery, BSS is battery energy storage system. That's good. Thank you, Yushra. So it needs to gather information from maybe from wind, solar, and so on. It needs to predict, gathering data, yes, and then using data from what we had, predict, then aggregate different, we don't know from which direction the wind is going to blow. Then you can have a focus on what the DG output is going to be. And this is a focus itself. This focus is going to be used in another focus for demand focus, which is itself a function of plan generation. You see, so many uncertainties in the process. This is what makes it complicated. Now, if as I was telling you, you need to balance supply and demand. If you don't manage supply and demand, what's going to happen? This is where you're going to have disturbance on your network. Okay, this is just to appreciate the problem which is happening. So power grid management is state-of-art computerized control centers. Or a control center is not about receiving information from the power station. It's about getting information, maybe using pulse information, and then information from the weather station, to use all these, and then maybe using numerical method and so on to be able to forecast what will be the output from the wind farm, output from the wind turbine, output not only from the major wind farm, but from the distributed one that you have on your neighbor's house, the rooftop PV that you have on your house, and so on, trying to adapt all that to be able to predict the demand and supply balance, how it's going to work. So lots of stress on this part as well. And then we have what we call, I won't spend too much time on this one, which is what we call the okay. So this is what we call the duck curve. Okay, the duck curve. Why? Because as we are increasing, basically, this is a normal power curve here, what you have every day, most likely. Okay. Now, when we are going to introduce PV, photovoltaic, it's going to be like this. Is I'm just going to draw the supply. This is during daytime. This is role of PV. If you have 1 gigawatt of PV, if you have 2 gigawatts, this is 1 gigawatt. If you have 2 gigawatt, what's going to happen? This one is going to be up. So the net, this is PV, the power input from PV. As you increase the amount of PV in the system, what's going to happen? This is going to be your resultant graph, because you don't need to produce so much of power. You are producing this. Ultimately, this is going to be remain the same, but you are not producing actively from your current power generation. This is injecting from the grid. We just check the chat. Let me just check the chat. Okay, let's focus now on our thing. So who is in? Those who are in are going to remain in. Those who are out, unfortunately, they will need to watch the recording. Okay, so what's happening as we increase photovoltaic injection in our system? What's going to happen? The curve, the contribution from the traditional power system is going down, because we are having power contribution from PV. Ultimately, this is where we are going to find ourselves when you have around 8 gigawatts. This is a study, I think, for from the US, okay, from California. This is what is going to happen. Okay, this is where you around sunset, where power is going to go up. Now, the beautiful, not the beautiful, but the ugly part is that having this ramp, this is where you need to have conventional power to ramp up. This amount of power, you can't have it from power system. It needs, conventional power system needs power, maybe 1 hour to run before, okay, to get it ready to be available on the grid. So you can't have this like d by dx, this gradient, you can't have it. This is what we call the duck curve, okay? And it is an issue which most likely we are going to tackle. You can see it takes the shape of a duck, but we call that the duck curve, and it is due to high penetration of wind, not wind, but PV in the network. Let's have a look at the generation. This is the output from a 9.35 megawatt wind farm that we have in Mauritius. We have only one in Mauritius, a huge wind farm like this. Not huge, but relatively speaking. Okay, so MB, this is how the power looks like, day 1, day 2. So you can see that it's difficult to predict. And every day is going to be like a different, maybe, shape of the graph. This is for wind. How about PV? Okay, this is how it's going to be like. For 7 days, it's different for each and every day. You can't like predict precisely what's going to be like. Okay, so this is it for wind and time. Okay, this gives us this picture. We have the wind output and the solar output, which we can't predict. We can have an average, that would be fine, but then predict precisely how much power is going to be. So what is the technology which is going to help us now? We have battery, what we call BSS. Okay, so the battery is going to have, just like this one, let me just draw it, excess power. Okay, we just keep this one, this is, we're going to use that, and then this one. The excess here, we are going to use that to charge the battery. And when we need it, okay, maybe this is the power. We need power from supply, from the battery. We are going to provide battery back to so the battery is going to provide power to the grid. So it's charging and discharging so as to nullify, to remove these grid and to make it like more more flat, more acceptable to the power system. This is like a simplified approach. It's not as easy as that. Okay, this is how we can use battery energy to do this, like what we call flattening of the curve and so on. Next, so this is about energy, but BESS, as we mentioned, has the capability to take from the grid, store, and then discharge. Okay, anyway. So to take, store, and discharge energy on command. When we want, we can just, or we can put an algorithm in there. When they need, they can easily do that. Okay. Benefits to the grid, you have a few which you can read. And then it is not, how can I approve this one? Okay, anyway. Okay, so pump hydro station, okay, it was, energy storage was not like something which is new, okay, it is something which has been used before, which has been present in terms of pump hydro, which is another technology. I'm just mentioning it here. If you're interested, you can read more about that, but it is, oops. Let me just remove. Please don't change, okay. Okay, so pump hydro has been used before, but then nowadays we are more going towards what we call battery energy storage. We can store battery in terms of DC power. This is a traditional how. Let me just check this one. Why? Okay. Anyway, this is a traditional way by which our power system, the traditional load demand of the day, okay, how it was now. And we can use, so this to be able to supply these, but because the peak load is difficult, because this is where we need to have a few engines on, and it costs a lot of energy for that. To put an engine for a generation set for 2 hours or 3 hours, this costs a lot of energy for the power utility. So what can be done? Here you can see it is like nil. So you can use energy, you can store this energy. So you're going to generate maybe somewhere around here. It's going to be like fixed. And then, so you can just shift this down here. So you store energy, and when you need it, you give it back to the system. So it's about charging and discharging, how you can use battery energy storage to maybe make your system much more efficient. Just a few minutes to review. Just checking the chat. Can you wait? Let me just clear this one on the date, clear. Let's focus. So ultimately, we have the virtual power plant. So what's coming up in the virtual power plant? It's a lot of new things. So you have seen, we have wind power. We have discussed a bit about solar power, decentralized, or these are the decentralized power plant, all these, the hydroelectric plant, bioenergy, emergency power system, okay? And then you have the customers, or it can be what we call the prosumers. We have seen heat production facilities, if we have, in some countries we don't have, energy storage, cooling production facilities, only a few around the world where they store energy in terms of coolant, okay, and cooling. And then what's happening? External information, okay, plant availability, those information. A new one here is about the trading system. Okay, this is going to bring about what we call a trading system in power system. It's going to be like what we call a marketplace. So let's read through that. The wholesale market will be much more dynamic, volatile, and complex, and will create new opportunities for traders. The negotiation for buying, selling will take up the level of domestic customers. It's going to be peer-to-peer. So I want to buy electricity from you. Can you do that? Right now, you can buy only maybe from the distribution, what we call a disco distribution company. Okay, but can I say, okay, I want to buy it from my friend over there who's producing from his rooftop? Yes, you will be able to do that in the near future. It's what we call a wholesale market. How is that be happening? So we have enabler, which we call blockchain. So blockchain is going to be in form of cryptocurrency as well as commodity trading. It has this ability to be able to provide this one. It is, or it's not something new. It is already on the energy market, and it's going to increase based on what Global Markets Insight says. It's going to increase from currently in 2018 around 200 million USD to 18 billion USD in a couple of years. So it is already here, and there are already some documentation already on that. I'm leaving the links here, which will be circulated to you. You can read about that. So blockchain is going to be 10% is going to be used for metering as well. Grid management 20%, 40% for distributed generation. What we have just been looking, rooftop PV and so on. Electric vehicle charging 20% and 10% for Internet of Things. Here it is, Internet of Things. We will be able to control, let's say at night, this is where, like at the peak, the evening peak, where power produced is more expensive. So can we say, okay, I can switch off my refrigerator, or I won't be putting my washing machine on at this point in time. So right now you may add a timer and so on, but nowadays with IoT, Internet of Things, you would be able to control each and every equipment in the house. Not only you, but you can give the permission for a system, okay? Maybe a group of company who can have, if you want to bring down your cost of energy, you can get to this system, and using Internet of Things, you would be able to control your equipment on an individual basis. So you can use what we call Internet of Things, blockchain, and it's partly in terms of big data as well. Now, this said, what's going to happen? Okay, this is very good, very beautiful picture. What is the problem that is going to create? Okay, even you have two technologies, it has good advantages and disadvantages. It's about the disadvantages about cyber security threat. You can have hackers who can get to your system. Now it's about protecting. So this is a use of IT. IT in terms of the power systems is going to protect our power system. So you will need to put barriers and so many of infrastructures in place to be able to secure your power system. We also have microgrid. So microgrid is a group of interconnected load. Let's say in a small village or in an area, you have lots of maybe distributed generation, a few solar panel, a small wind farm, and so on. At one point in time, you can decide, or the grid can decide, okay, you can disconnect. So you operate as a small micro. You're not connected to the main grid. You can operate on your own. Okay, so this can be achieved nowadays with what we call microgrids. There's a lot of controllers needed. It's not something like readily like so. You need to control because you need to manage your frequency and the supply and demand on your grid. Definitely, you will need to have a battery to be able to take up for that. Not battery, but that is a storage device which can be put online at any moment in place just to control the supply and demand. So this is about microgrid, which is in some countries it is happening. Most interestingly, we have it in large universities, campus, and so on, military bases. We have one which we call a microgrid, DC microgrid. Why DC microgrid? Okay, we have a grid, let's say in some countries, we have it mostly in Africa, 4 countries which are very far from we don't have electricity because it's going to cost a lot to bring electricity from the mainland, maybe the cities, towards the remote villages. So they say, okay, but let's build a small grid. Let's put PV panels so we wind farm. We can get electricity for our basic needs. That's good. So they say, okay, we are producing in terms of DC. We are converting that into AC. We are transmitting it shortly in a short area, small area. In AC, most of our load nowadays, your PC is using, it is supplied with AC, but it has a converter which is in DC. Your mobile phone, it is in DC because you have an adapter which is converting that to DC, but a lot of load can work on DC. So why need to convert from DC, AC, then back to DC? Can't we have a DC microgrid? So there are some research which are being driven to see whether a DC microgrid can be implemented in such areas. Okay, so you can, if you're interested on this, I invite you to read more and more about that. So we are nearly in 1 hour. Let's see how much more we can cover. Okay, electric vehicles. So this as well is going up. So from 5.1 million in 2018, expected to grow to 130 million by 2030. Okay, so is it a challenge or an opportunity for the grid? It is, because the grid is already overburdened. At times in some countries we can't meet, the supply can't meet the demand. Okay, we are already in a critical system. Okay, so this is a challenge, having more and more of these cars, truck, buses, even metro, okay, connected. So it's like an electrification of the transportation system. But then what is the opportunity? They have battery, which we call moving batteries. Can we use that for load leveling? As we said, during the day, we can charge them, and during the night, when most of the cars are in the garage, people are in the kitchen and so on, preparing dinner, watching TV, they're not using their car, we can use a battery to discharge to the grid. This is where we need more power. So these batteries can be used to discharge in the grid, okay? And then at midnight, where everyone is sleeping and so on, no major output from the grid, these can be used to recharge the battery in the car again. So is it something that can be done? Theoretically, yes, but you have lots of policies and regulations which needs to be able to, because when you're charging and discharging a battery, the lifetime is going down. So how can we, what can be the tariff? So these are things that needs to be looked into. Okay, again, there the link. If you need to read more about that, you can have a look on that. So maybe I will, let me just check where I have reached. Let me just share the, okay, I have maybe some 15, here we are. Maybe some 15 minutes more, I think should be completed. Okay, I'm just going to rush, maybe give you only the idea, then you can have the PowerPoint later on, you can just to have a bigger picture approach. So this is the man driving his diesel car. He feels so dirty. Then he said, I'm driving an electric car, which is being charged using conventional power. Is he really clean? But the best way is to charge using renewable energy. Then you can say, yes, this is like clean. Okay, next move to the next. Give me one more minute. What happened? I'm not able to see anyway. Okay. Just give me 1 minute. Okay, there we go. Okay, so active management. So we have been discussing a lot about generation, distributed generation, battery energy storage. So it's about supply of power. Let me at least take one example for dynamic line weighting about the power system. Okay, basically, you know this equation from your engineering degrees most likely. Resistance is a component of the resistance is depends on temperature. Okay, if temperature changes, our resistance is going to change. And resistance is going to define how much power we are able to, how much current is going to flow. So how much power. In our calculations, when we are designing a line, we are going to take the current ambient temperature. We are not going to vary the temperature. We're going to measure. We say, okay, in this region, the temperature is on average, maybe 25 degrees C. We are going to use that, and it's going to define the current carrying capacity of this region, of this conductor, and of this line. But nowadays, just remember, if you're able to see, okay, let me go through this slide. By monitoring the environmental conditions of the power line, okay, the actual capacity of the line can be assessed. So if, let's say it was designed at 25 degrees C, so you know what will be the current carrying capacity. If now it is cooler, remember our equation, if it is cooler, we will be able, the resistance is going to be smaller, and then we are able to carry much more power. But we need to have information from the field. What is the actual temperature there? Previously, this was not possible. Nowadays, we are able to monitor these types of conditions. You install these devices on the line, they're going to transmit information in real time, and you will be able to know that the transmission capacity of a line is not static. It's not written on paper. It is dynamic. It's going to change with changing temperature. So you have a whole power system which is dynamic nowadays. Okay, and this can help because let's say you have a wind turbine. So more winds means higher generation capacity, and more winds means your conductor temperature is going to go down. So you are able to evacuate much more power from these wind turbines. These are a few examples that you can have. So it is based on real-time monitoring. You need mobile network to send the data. A server, here it's about IT, big data, getting all this information in, processing that and putting that in what we call a GIS application, which we are going to see. This is a traditional way on paper, we're drawing network and so on. This is what we don't need that nowadays. We are looking for a GIS, geographical information system, which is organized in terms of layers. We have a base map, then we can put our network onto that, maybe the street map and so on. Ultimately, we have our network, different layers, and there you can place your maybe sensors and so on. So you can have layer for transmission, distribution, and so on. You can do planning, so many things that can be done using the GIS. We are trying to set up one for Mauritius. There are some countries which have already done so. We are trying to put, because we are using our own resources, it's taking time, but we are trying to do our own in Mauritius. So you can access that from your mobile and so on. So it's very interesting. And so it's good. You can use it for customer service. You can use it for planning, for SCADA, anything. Okay. So else you can use drone technology for power line. Okay. Again, use drone instead of sending people to do the inspection where you need to shut down power. Drone can do the inspection in real time without the need for shutting down the line. So this is going to decrease operation and maintenance costs for line inspection. Okay, we can use even infrared camera to be able to do predictive maintenance. I think I have a few pictures here. This is for vegetation management, where you can use a drone or a LiDAR, what we call a LiDAR, to be able to see which trees are growing too close to your power line. So you will need to have maintenance. If you don't do that, a drone can do that like in 1 hour. Okay, if you take it, remember 1 hour characteristic is to regulate operation and maintenance costs, because it's going to be passed on to the customer ultimately. A small inspection can cost you like 26,000 Pakistani rupees per kilometer, just having someone to walk around to do the inspection. Okay, this is how much it's going to cost. If you say, okay, let's use a LiDAR using a helicopter. So this is another option. So this is going to decrease, of course, is going to be around 14,000 Pakistan rupees per kilometer. But now if you use a drone for the inspection, this can bring down the cost to 10,000 Pakistan rupees per kilometer. Ultimately, from the traditional one, having someone go on site to do the inspection, it can bring down the cost by 61%. Let's say 60%. So you can bring down the cost of operating your network down with these type of technologies. Let me just check my time. Okay, let's run quickly through that. Advanced distribution management system. If you have a fault happening here, okay, what's going to happen? This line is going to be off. These are remain in operation. So these people here are going to remain without power. So what can be done nowadays? If we automatize these, we have breakers and so on the system, which can automatically see that there's no power. They have intelligence, artificial intelligence. They can know which part has power. So you can write this programming right now. And I know that from student, okay, you as student, you can already use this type of programming. But what was the barrier was how to implement that in practice. Nowadays, we have technology, communication, and these which can help us. So what we call a self-healing network. We have a fault, the system won't need intervention on the side. It can self-heal itself based on programming that we have done. It's going what we call a robust network. Automatic reconfiguration, fault management, all these are common terms which are related to what we call the ADMS, Advanced Distribution Management System, or what we call Advanced Distribution Automation. It can be used for outage management, and the response time is going to go down. Remember, we talk about reliability, resilience, and so on in the beginning. So these are going to decrease the response time. So frequency and duration of interaction is going to be before a few seconds. Then the network reconfigures itself automatically and power is restored to all customers. All customers in this configuration to all customers. Then the repair team can come leisurely repairs the fault. Okay. We then have flexible AC transmission system, which we call FACS. Okay. They add what we call flexibility. That's why it's called flexibility. They add flexibility to the system. So they can add what we call capacitor and resistor to the system. So not capacitor, but capacitor and inductor to the system to be able to regulate voltage and different parameters in the network. So they can do that instead of having an intervention, human intervention, they can do that automatically using different maybe sensors and so on that you have. So it's about power electronics and electric devices which can be used automatically, installed at specific points in the network, especially long network, okay, where they can regulate the line much easier. So you have added flexibility. Last one for distribution, so at metering. Hopefully you know about this one, the electromechanical meters, okay, that has been around for so many times. Ultimately, with time, it is a mechanical, it's going to lose its movement and so on, and it's going to record less power. Okay, so if it is consuming 10 units, after 30 years, going to maybe only 9 units, which is going to be registered. So utility is losing 1 unit. But if you multiply that by how many customers you have, it's going to be huge. This is contributing to losses as well. These are non-technical losses. This has been replaced by electronic meter, which don't have this issue of the values drifting with time. But then we still have what we call automatic meter reading. There's no need for a meter reader to be on place to read the meters and so on. So you can have it through, you just input a SIM card over there, it's going to send the information to a network. This is good, not bad. It can be called a smart meter as well. But what we are looking for is the customer knows about it. Okay, this is a screen, it's a new one, okay, where people say, okay, my consumption, if you have different types of tariff, maybe a tariff during the day, during the peak and off-peak hours. So this is a peak hours, energy is expensive. They will know from here how much I have used and so on. So they can regulate their consumption in their house, or they can have a software to regulate it automatically. This is room for research, room for improvement. This is what we are looking for in the near future. It's not only in terms of technology. All these that we have been mentioning are room for research, which is going to create jobs for you in the near future. Renewable itself is going to add so many of new jobs for you. It's not going to, as we said, technology, people are losing their jobs. No, it's creating jobs as well. It's up to you to know in which sector you are going to invest. Now, quick look at concerns. First is harmonics. We have so many with digitalization, heavy use of electronics, non-linear load. Remember, we had only motors and fluorescent lamps in the past. Nowadays, we have CFL lamp, fluorescent lamps, and so on. We had incandescent lamp. Now we are using fluorescent lamp. Fluorescent lamps, they are using ballast and so on. Motors nowadays, they have drives, okay, motor drive with power electronics, so you can control the speed. This is so good. But while you are injecting, you are incorporating drives in there, you are putting power electronics. Power electronics is contributing to harmonics. So harmonics can create what we call quality problems in the system. Now, how about resilient? We talk about climate change, and this is what can happen if we don't. So is our network ready for maybe wildfires? We have it in Australia, in the US, thunderstorm, okay, with so many pollution and so on. Is it like having like much impact in terms of our system in terms of thunderstorm? Heavy snow, okay, it is going to be more and more difficult for us. We need to maintain, to build our network in to be resilient to these conditions. Super cyclone, okay, this one is in Odisha in 2019. So how much time can we have our network back in time? Do we have redundancy in our network to be able to provide power to the area, even though we have a cyclone? Do we need to go underground? Okay, flooding. How is our system going to work in such situation? And it is commonplace nowadays, not only in one country. It can happen anytime you have flash flood and so on happening. Even here, a whole substation immersed in water in flooding. Okay, we are talking about big terms, smart grid and so on, but if we are not prepared for these situations, how will we be able to supply power to people? Okay, so things that we need to be careful about, which we are not going to talk about, our regulatory body. So many things happening. We said it's like an energy market. We need regulators to help us in that. We have the members of hackers and so on. We need to have policies in place. Maybe the laws needs to be amended, and it's going after all to become like a big industry. It's not only one or two players like the utility producing, transmitting, distributing. It's about us nowadays, consumers and producers. We are going to be party to that maybe change which is happening in terms of modernization. Okay, this graph I'm going to leave is that to you. Okay, this is going to show you in terms of meters. You can interpret that maybe at your own pace in terms of meters. So this is what's happening on next to the customer. Okay, the customer needs to take care of harmonics, maybe using filters. Next, in terms of the distribution, we need to have voltage regulation, maybe FACS as well, how to take care of the distribution feeder, interconnection of distributed generation. Then this is in terms of the utility. Okay, that is on the bigger grid. What can happen? Congestion on the transmission system, renewable sources, bigger one. These are for California utility. Don't worry about that. This is for the bigger district in the US. So this was in terms of meters. So how far are you from the customer upward toward the main, the traditional power system? What are the different things which needs to be looked into for planning? Now, in terms of seconds, what things do we need to take care of right now and in time, which is more important? So high frequency switching devices. So this is happening in terms of microsecond. Okay, cycrophasers, protective relay. Okay, protection is going to be very important because we have it's not only unidirectional but bidirectional nowadays. Remember, we talk about that. So our protection system needs to be careful about how we are protecting our network, and dynamic system response is another theme in itself. Maybe next time we can talk about that. Automatic generator controls, a variation in PV and wind, we talk about that. Demand response, a theme in itself. Service restoration, we touch on this a bit. Daily ahead scheduling, how to forecast, we discussed about that. T&D planning, how to plan for new infrastructure coming up and how we are going to meet our carbon emission goal. We started with that, the decarbonization, the Paris Protocol, Paris Agreement, and so on. And ultimately, it is form part of it's going to drive us towards a goal we are trying to achieve in modernization. So quickly, we'll have a look at modernization, the need, drivers, enablers, then the generation sources from distributed generation, from BSS, and I think distributed generation and renewable energy. Power lines, we discussed about, if I'm not mistaken, about the active management of power lines, the drone, how to decrease operations and maintenance. Using only one example about the drone, we have been able to decrease operation maintenance costs. So we have many more which we need to look into. A few of the concerns, being resilient to the weather, which is changing, okay, and then harmonics, which is going to be a major issue in the coming years. And then we conclude that, okay, it's like a bigger picture which we need to look at. It's not only one or two things, but it's like an industry which is growing up to be able to power up this next generation of power system. So that was it from me. I think I've taken slightly more, but around like 90 minutes. So if you have any questions, let me just check. Do you have any questions that you have in the chat? Yes, so let me just hide this. Pause the chat. So the recorded session is going, I'm going to send that to Fatima, okay, and the slide as well. And since they have your what we call email address, is going to, you will be able to have all that with you. Okay, I think it was mainly about removing those who were creating a bit of disturbance. So anyway, let me just share the last slide with you for you. So, oops. You have my contact details on this one. Okay. If you need more information, okay, my email address, you have it. and no need to call me. So you can address me if you have any specific questions. Okay, you can just let me know. You can send it to me. So anyway, I think maybe there were a few interruptions in terms of the connectivity. Maybe you could not hear me at one point in time. But anyway, if you have any questions, you can just, I don't see anything in the chat box. Okay, let me just check. Okay, so anyway, maybe Abdul Rafiq would like to say anything.
Yes, sir. Thank you so much for your time, and thank you so much for taking up the time. And it was a very informative session, as well as for the members also. And so, shall we end? If there is no question, anyone want to ask any question, to let me know.
Okay, don't think there's any questions, but
Yes.
I'm open. You can send me an email at any point in time. So I'm going to send you the recording. So I'm going to upload that on YouTube, yeah, and send you the link, and as well as a PowerPoint slide you can share with the participant. So it was a pleasure. Thank you for having me, and looking forward to meeting you maybe in the near future. Thank you, everyone.
Thank you so much, sir. Thank you so much. Take care. Bye.
Bye.